So here, what we see here is the chip manufacturing process, starting from extracting the sand and creating a silicon ingot until the chip is get manufactured and packaged and shipped to customer. So what is the process involved? Let's give a quick and short uh, understanding here. Okay. So the last time I remember I told you guys we need the semiconductor material, which is a silicon that we are using as a base base substrate on which we are trying to build our circuit, either in the CMOS design or by CMOS or any other advanced fabrication methodology. Okay, so silicon is a base, and we need silicon wafers. On silicon, on top of the silicon wafers only, we will be able to bring up the process of all the logical gates. If let's say if your SOC is having the mobile SOC is having around 4 million or close to 10 million or 200 million gates, all these gates are brought up at that particular technology node of 1 nanometer or 2 nanometer or 5 nanometer, whatever the technology node. Okay, so all this will come up after you have a I mean, the basic input that you need is the silicon wafer. Okay, so the sand, by heating the sand at a certain degree of heat, that heat the sand, and we bring out the unpured silicon. Um, and on top of that, we do a lot of what we call purification process happens, and we pour them into a molds, and the mold will be in the shape of the cylindrical shape that you see here. These are the molds, and once the hot silicon, the pure hot silicon is poured into in the molds in these shapes, cylindrical shapes called as ingot. Okay, they will be sliced. So silicon ingots will be in like 8 to 12 in diameter and 12 to 24 inch in long. Okay, so these are in the inches, as you can see. Next, the slicer, the this is all done in a manufacturing unit, right? So the next process would be the slicer, which will slice this ingot into thin, like 0.1 inch thick. Okay, 0.1 inch thick wafers. Okay, so once the wafers are these are blank wafers. Okay, once the blank wafers are done, and we need to convert them into the pattern wafer into the size of your SOC or your chiplet that you want to be. Okay, so generally industry uses the standardized chiplet sizes. Let's say Intel, if it is Intel CPU, Intel processor unit, or a Intel SoC, AMD, Qualcomm. So every standard company for a processor or the RAM or the graphical processing unit or any digital IC that you see, okay, that has the required size, and they follow a standard. As per that size, the chip size, okay, this wafer will be diced. Okay, so this is something like this chip manufacturing process is done by the manufacturers. So the fabless companies like Qualcomm doesn't has a fab, Nvidia doesn't has a fab, AMD does not has a fab. So they go to Samsung, Intel, or ASML, or TSMC, okay, Global Foundries, to get their ICs manufactured. So when they go to these manufacturers, so they give the schedule of uh, for that particular SOC good to be uh, what we call packaged and tested at first, the initial testing, packaging, and again the testing and shipping to customer. So this process is predefined, and the size of the chip is pre-configured. Okay, based on that only, this will be segregated in the size of your chiplet. So, however, in a wafer, in a round wafer, if you exclude these corners that are not pure boxes, okay, these are useless. Okay, so only the middle ones that you see here are useful. Okay, and in even that, even in this particular dice, these are called, each single box is called a die. Okay, so individual dice. Okay, so each die in a wafer, okay, with a proper uh, meeting of our requirement. So each die will be tested as per our requirement. Let's say this is a silicon wafer, right? So is it 100% or close to 95 or 98 or 99% good silicon? That means if you bring up your IC on this particular die, will it give the efficient results? Okay, so uh, that will be checked. Okay, and in this stage, die tester. So out of all these dies, okay, few will be cross marked, and these are bad dies which will not be useful. So if you take a wafer with 200 or 300 dies, okay, here we are showing in a small size, but it will, in real time, it will be very big. So in it, 200, 300, or even if you consider it as a 40 or 50 dies, most of the dice will be in a bad shape that you cannot bring up your IC there, because it is that particular die, the silicon is not properly uh, um, is it's not proper, the connectivity is not there properly. So there could be many process variants and temperature metrics it is not meeting. So you will discard these bad dice, and only the good dice will be moved into one die to packaging. So if you see a proper in a motherboard or a computer motherboards, if you see, you'll see the package. Okay, on top of die there will be black package, right, with pins. Okay, so it's a quad flat package. You can see the pins are on the four sides of the IC. So like this, and again, once the packaging is done, it will be tested. Okay, even after packaging, if it is not meeting the criteria, it is not behaving as per the requirement, again that will be discarded, and only the fine and tuned uh, tested, okay, dice will be going to customer. Okay, this is the general process. It is in a shortcut. There will be much more elaborative process in real time, which we don't need to worry about. Okay, that you can learn part of your technical growth. Moving on, you see here, this is a wafer of a Pentium 4 processor. We have this Pentium 4 in 1998, and till 2004 we had Pentium 4 processors. Okay, so this is Intel's Pentium 4 processor, and it is, you see that it is 8 inches 20 centimeters in diameter, and the die area is 250 square. So generally your dice will be measured in terms of millimeter square. Okay, 250 millimeter square, about 16 per side. Okay, so in this particular die you have 55 million transistors. We are talking about an IC that got designed in 1998. Okay, and transistor count that you see is 55 million transistors per die. Imagine the current ICs, okay, on a die, how much transistor count you are expecting. Okay, it will be in terms of billions and trillions as of the moment. So it is in a 0.18 micrometer, that is a 180 nanometer technology. And the size of smallest transistor, okay, improved technology uses 0.13, 130 nanometer and 90 nanometer. So dies per wafer, on a per wafer here, as per this die area, we have got 169 dies for a 8 inches wafer. For 8 inches wafer, you have got 169 dies. And you see, when yield is 100%, that means out of 169 wafers, 169 dies, all 169 dies are tested okay, and they're good ICs or a good dies, then you are getting 100% yield. Okay. So number is reduced after testing. So your yield number will reduce after testing. So if you see, you have assumed it to be, I mean, not assumed. In industry, nothing will be assumed. Okay. Uh, as per the wafer section, segregating your dies, you have got 169, where the yield is 100%. And after testing, you'll come to know if there is any bad IC and your yield will reduce. So it is also the manufacturing unit and the efficiency of the tools and the process. Okay, depending on all of these parameters, your yield will be high, and your DFT plays major key role in yield. Okay, the DFT came into picture because of the yield in the first place, actually. Okay, so number of ICs that are being manufactured by any manufacturer, the number of ICs getting manufactured, out of that, your probability of good ICs is less. That means your yield is less. Okay, so it is a ratio of number of good ICs detected by the total number of ICs manufactured. So your yield should be high. For that, whatever you want to do, you need to do. And DFT came into picture in the first place because of the yield. Okay, so all the silicon, I mean, in the back end, the manufacturing devices are also getting into good shapes. Even the silicon wafer creation is getting better and better day to day. Okay, so after the wafer is tested good, okay, and you started inserting your design, bringing up your IC design, everything, and when you are testing it again on a real design on the chip, then it should pass. For that, DFT plays a crucial role. Okay, so rounded dice at boundary are useless. Rounded dice means here, as you can see, the corners, all these corners which are not in a square shape or whatever the die shape that you expected is not meeting, then all these are useless. So as I was saying, okay, out of 120 dice, removing all the round corners, 120 dice, only 1 or 10 are good. Okay, and here out of 26 dice, 15 are good. So this, the good or bad, depends on your process variance and temperature metrics and the IC quality. IC quality in the sense the design quality. So yield is equal to number of good dies by the total number of dies. Okay, and your die cost is equal to wafer cost by dies per wafer into yield. So this affects the manufacturer a lot. The wafer cost is too high, because extracting silicon out of sand and making ingots and slicing it and creating a wafer, you know how much it costs? A single wafer costs you close to $200. Okay, so $200 for a single wafer. So on a larger scale, okay, the manufacturing equipment to do this process, okay, the manufacturing equipment costs you around 100 cr. Okay, so the semiconductor equipment and manufacturing devices are too costly. Okay, very precise, is equal to, I would say, more than designing a satellite. Okay, um, and the chemical laboratories, semiconductor fab. If you go inside, I have been to semiconductor fab many times, and as I am currently in an area where we regularly go to the fab, you need to suit up completely. There will be uh, zero zero uh, impurities or air impurities, dust particles, nothing in the air. Zero. Okay, lab should be in such a condition that there shouldn't be any dust particle roaming around the air or from your body or from suit or anything anywhere, which could damage the entire lab. So your lab is maintained with a zero dust particle. So if you are seeing a Pentium 4 processor, this is your block diagram of your entire chip and the implementation, the physical implementation. This is your chip. You see this? This is your chip, and this chip is comes into one particular die. Get it? Understood? Clear?
Sir, what does yield do, sir?
Yield is a measuring number. So if you, let's say you are uh, mm, you are manufacturing uh, pencil or a pen. Let's say, assume you are a pen manufacturer. Okay, you are manufacturing 100 pens at a time using some equipment, and out of 100 pens, while in the process of manufacturing, you end up getting only 50 pens in a good shape. So what is the success ratio? Out of 100, if you are getting only 50, what is success ratio? How much is the loss?
50%.
Right. So 50% is your yield and 50% is your loss. Right? So similarly, in a manufacturing unit, in the chip manufacturing process, if your 100 ICs are getting manufactured and only 50 ICs are in good shape after testing, everything is done and ready to send to customer, after all the testing is done and finalized, you end up with only 50 ICs which are in good shape and working as per the requirement. Let's say you are having the CPU clock of 2.4 gigahertz, you are meeting that, your voltage, current, all the metrics, all the PVT corner metrics you are meeting. Okay, and you're having only 50 outcome out of 100, then you're having 50% only yield, which directly tells you that you have 50% loss of a manufacturing process. So that is very high for a manufacturer. He loses a lot. Okay, understood? The yield, you got the point of yield, right? You need to calculate, right? So end of the day, you're a manufacturer and you have to know how many you are getting, how much you are investing and how much you are getting out of it, right? So you need to measure it, right? So yield is a measuring formula that you, it's a basic simple formula. Out of 100 manufacturing, you are getting how many good ICs you are getting out of it. That's a measuring formula. We call it as yield in any manufacturing process, not just semiconductor. Yield is a term used worldwide in any industry, any manufacturing industry. I have given you an example of pen or pencil manufacturing, right? Even there, we'll have it. Clear? Can I move forward? Any queries? I'm not hearing any voice. Those who raised the question of yield. Is it clear, or you have still have any question? Check if you're in mute. I'm not hearing anything.
Yes, sir. Understood the process.
Thank you. Thank you. See, while I'm presenting, I will not be able to see who is asking question. Okay. Uh, as we are new batch, I still don't recognize the voices. Okay, I can differentiate between a girl and a boy, but I cannot recognize the voices of people yet. Okay, going forward, we'll do that. So here, as I said, this is your physical implementation of your chip, and this is your digital block diagram of that. So this is your control unit, one more control unit of different. I mean, this is controlling something else. This is controlling something else, and this is your instruction cache, and this is your enhanced floating point and multimedia module and data cache, integer data path. Again, another control unit, advanced pipelining and hyper-threading support, one more control unit, secondary cache and memory interface. So these all are, I mean, this is a Pentium 4 processor chip. So this is a processor. What does a processor has? ALU, memory unit, control unit. Correct? The basic computer, as you understand, right? So this is you implement it in a digitally. RTL code is written in this way, and we finally the physical design engineers and analog layout engineers and all the principal layout engineers work is to implement your digital logic, convert into gate level, and finally into the physical CMOS design or whatever the technology that you're using, fabrication technology. So moving on, we have a lot of technology improvements for the last few decades. Okay, so we have come up from vacuum tubes to transistors and transistors to digital 2D, 3D ICs, which are having what we call purely CMOS based PET technologies. Okay, so here when you say transistor is a analog transistor, okay, BJT transistors, vacuum tubes of BJT transistors, ICs, digital ICs, and finally it's a proper VLSI, purely digital CMOS designs. And the processor, I mean, this is, we did not stop it here. This is just a basics that you're learning. We have achieved much more technology improvements. Okay, we are just covering the basic fundamentals. Okay, moving forward, going forward, we'll be seeing where we are and what is the technologies, current technologies that we are using. So processor transistor count is increasing every year by 30% and 40% every year. Okay, so it's a drastic transistor count that we have at the moment. Luckily, the EDA tools that we are using are playing 80% of the role. As I said, 80 to 85% of the role, taking care of all these large designs. Okay, uh, the engineer has only one role to control the EDA tools and um, design your IC. Okay, so coming to memories, the DRAM capacity, the dynamic RAM capacity is also increasing about 60% per year. So it is much uh, too too much increase in terms of memory capacity. When we see from 2010, when we started with uh, Android device of Samsung within India, okay, and now where we are. Uh, when we started, I think it is around 500 MB RAM or 250 MB RAM. Okay, now we are in a stage where we are at 36 GB, and I think Samsung started making a 2 terabyte RAM somewhere. It is still in the process. Okay, we are improving the technology too rapidly. So we are at a high phase. Okay, and your cost per bit decreases about 20% per year. Means the RAM memory manufacturers, okay, like a Western Digital or a SanDisk or all the manufacturers, I mean, Samsung plays a key role in memory manufacturing, and Micron and all of this. Okay, their work is to reduce the cost, the design cost, and increase the efficiency, accumulate more memory space with a low power, multi-threading, high performance. Okay, so all each future uh, comes up with with the backup of a proper semiconductor engineer, the chip design engineer, in taking care of power capacity or multi-threading capacity, okay, or in the designing or architecting the memory designs. Okay, so chip design engineers play a key role in the digital era that we are in. Going forward, it is going to be 100% digital, right? Everywhere we will be completely digitalized, and digital means you are having IC, and IC manufacturing will be the common base or subject. Okay, even from the school. Okay, so disk capacity, as you can see, is also improvising a lot. We started with very less. I think we had in the year of 2002, I have seen we had 100 GB, and after that currently we are at how much 16 terabyte or more. Okay, the largest capacity that I have seen physically. Okay, so in the market, the memory, either in terms of RAM or ROM, is increasing 60% per year. Okay, opportunities are coming with the improvements and better organizations and designs. As you can see, there are many startups, and those are already the legendary companies working in semiconductor since decades are doing so good. Nvidia is doing very good in artificial intelligence ICs, bringing up, and Intel is competing now. Qualcomm is doing a lot better. Okay, likewise, so AMD, Nvidia, Qualcomm, okay, Samsung, they're doing a lot better. The Apple, right? So going forward, we'll be in a stage that we'll stop talking bullshit and we'll start talking about technology more in our regular basic discussions when you meet your friends, colleagues, or anybody. So the current generation, when they become 30, 40, 50 years of age, so who are already in the semiconductor or a software, they talk more about technology, less bullshit talks, right? So we are changing actually, because the technology is changing and we are catching up to that. So this is the growth, as you can see, from 1976. If you see, it's 16K. As I said, in 2002 we are at 512 memory. Okay, 512 MB, and now where we are, the basic mobile phone, the basic model is having 8 GB RAM now. So when we started at very the zero stage. Now we are uh, we have improvised a lot in terms of performance. Performance is more functionality when you're keeping adding up more functionalities and fast processing. Okay, this is end of your chip manufacturing introduction, the basics. Okay, so moving on, let's heads up to the design flow, ASIC design flow, types of flows in the industry, how do we work it out, how do we start, and where DFT stands in the process. Okay, so the content would be introduction to ASIC design flow and the design methodologies. What is the methodology that people in the industry use in different end products, and the common out of all methodologies, the common ASIC design flow we are going to witness, and how mixed signal ASICs are in the current designs, and submicron ASICs. What are the challenges of deep submicron ASICs? And we'll take some case studies that we have in OBC ASIC. Okay. So I'm not sure people are aware uh, about. I mean, in the theoretically, people read that ASIC is separate, SOC is separate, NOC is separate, FPGA is separate, and all this, right? So end of the day, you are designing an IC for a particular application that becomes your ASIC. It's an application specific integrated circuit. Application specific integrated circuit might be having an SOC, NOC, anything. Okay, and even you can call FPGA to be ASIC if it is intended for a fixed specific application. But FPGAs are not designed for a specific application. They do multitasking. How it depends on how you configure an FPGA to perform. So FPGAs are differentiated from ASIC. So you can call ASICs and FPGAs are the two categories that we have in the industry. Okay, so it means an integrated circuit designed for a specific application. An application could be a microprocessor, cell phone, modem, router, etc. Okay, so nowadays ASIC has a complete system on it, often called as a system on chip. Okay, so in the earlier days, we never had SOC. I mean, we did not design a chip intended for a specific application using entire system on chip architecture. Early days in the sense where I'm talking about 90s and early 2000. Okay. So these are the ASIC design methodologies: full custom design, standard cell based design, gate array based design, structured ASICs. Okay. So remember, guys, here this ASIC design methodologies, each one is a designation. ASIC design engineer. In real time, you're an ASIC design engineer. That means you're either uh, working on a full custom design or a standard cell based design or a gate array based design or a structured ASICs. Okay. When you say chip designing, you are either referring to RTL design engineer or a physical design engineer. Okay, the verification, DFT, and are all the add-ons that come part of the DFT, the ASIC flow. Okay, but end of the day, RTL design has to design, write the code, and physical design engineer has to do the layout and the placement. Okay, and make it in a CMOS design suitable to be brought up in an IC on a die. Okay, so these engineers work on full custom design, which will have each primitive logic function or transistor is manually designed. So this generally happens in R&Ds. Okay, we'll see that. We'll see each and every one. standard cell based designs are you bring up standard cell libraries for every technology node. Let's say we started with 180 nanometer, and we are now at uh, 1 nanometer, still ongoing. But in the market, 1.8 nanometer coming from Intel is the latest. Okay, in the industry. So every technology node changes, you need to design your standard cell libraries. So standard cell libraries comes from the manufacturer. Let's say the foundry business. Who has the foundry business? Who is your end of the day where you are going for your IC to be manufactured? Is your manufacturer. So TSMC or TSMC has a worldwide reach of around 60 to 70%, and the rest is shared by Samsung, Global Foundries, Intel, and many other not so popular fabrication manufacturers. Okay, so TSMC plays a crucial role. Everybody just goes to TSMC, even Nvidia or AMD, anybody goes to TSMC and get their IC manufacturer. So that means TSMC says that I have brought up my standard cell based designs or a full custom design supporting for any kind of a transistor at this particular technology node. You want a library, take this. Because let's say uh, I I'm in need of designing my IC, and I'm looking for a manufacturer, and I'm going to TSMC. Now TSMC says that I'm tying up with TSMC, and I'm the customer of TSMC. Okay. Now TSMC will give me 1.8 nanometer technology standard cell libraries and all the libraries needed to for me to start developing the RTL code and bringing up entire design implementation. Okay. So Foundry will give you that standard cells. Okay. So the foundries, majority of the foundries will hire engineers to work on standard cell based designs. Next is the gate array based designs. Okay, so your wafer itself is prefabricated with unconnected gate arrays. Okay, this is also rarely seen, but still happening in the industry. Gate array based designs and structured ASICs. Okay, so wafers are prefabricated with the standard cell library cells. So we'll see each and everything. Okay, every methodology, starting with full custom ASICs. Each primitive logic function, let's say the AND behavior or the clock gating cell, okay, or IO pads, all the combination logic functionalities. The standard, the primitive, these are called primitive logic functions. The primitive logic functions are the that are called primitive. The meaning primitive means without them you cannot start. So those are the basics. All the AND gate, OR gate, NAND gate, NOT gate, all the logical gate functionalities. Okay, and the transistors which are manually designed, customly designed. So manually manipulation of each transistor geometry is done, so-called polygon pushing. This is called polygon pushing. We are not using this. This used to be the case when we started uh, designing ASICs. This used to be the R&D of bringing up your ASICs in the early days. Okay, so that is why it is rarely used. Uh, Advantages: it gives most optimal design, high speed, low power, small gate count, because everything is customized. Everything. Okay, so this is generally done in a R&D. If if you are coming up with a innovation with a perfect design, you know what in and out of it, and you want that to be designed customized by yourself, then you will have the benefits, advantages of high speed, low power, and small gate count. Design disadvantage would be, as it is R&D, you don't know how long it will take up, the long design cycle. So design cycle will be long. Okay, So each innovation takes up close to, in the earlier days it used to be decades. We have come up with years and months now. Okay, decades, years to the months. So if you are bringing up innovation in the semiconductor design, okay, in terms of any sector of a semiconductor process, you are bringing in innovation, okay, and coming with a high performance computing IC or a processor or something, anything, okay, that is taking only months now, okay, from decades of R&D. So even still, at the moment, you can say it's a long design cycle, because let's say your 9 to 10 months you were taking for innovation, and your general IC design cycle is now just 4 months. So you have a 5 months or 6 months additional wastage. So you- it's up to the company or the organization to waste that time, money, and the resources you pull in to design this. Okay, so that's full custom ASIC disadvantage, but it is expected. You want to do an R&D, it is expected. So higher NRE, non-recurring engineering cost. Okay, so non-recurring engineering cost is very higher, very high, because you need load more resources. Okay, moving on. Standard cell based ASIC design, as I said earlier. Okay, so everything is prefabricated. So predefined library cells. Okay, designs are created using schematic capture or a synthesis from hardware description HDL language. All mask layers are customized transistors and interconnects. So this is more suitable for designing memories. Okay, uh, memories or individual IPs. Okay, the advantages are shorter design time compared to full custom cycle. True. Mega cells or hard IP cores, microprocessor, Mac memories, etc. provided by vendor can be used easily because it's already done, designed. You just plug and play. Disadvantage is separate fabrication mask is required for each design, which will cost you more, very high, because end of the day fabrication unit has to provide. The manufacturer has to give you this, whatever you do. Gate array ASIC. So wafers comes up with a prefabricated with unconnected gate arrays. Your connections are not formed, but you have transistors filled up. You just need to form connections based on your circuit. Uh, so top metallization for connecting transistors is done according to different design at last stage. This is also very rare. Okay, it has advantages of lower NRE cost, because as base wafer comes with prefabricated, you need less resources and low turnaround time. Disadvantage is that low layout density, okay, and less optimized, which is very low speed, high power consumption, okay, suitable only for lower volume products like um, I would say in your home itself, you will see AC, washing machines, okay. You don't need to worry about speed. It's just FSM. It's a finite state machine. Just you have a predefined stages. You just program it and execute it. Small ICs. Structured ASIC. This is the one that we use in the industry. A structured ASIC falls between a gate array and a standard cell basic ASIC. The design task involves mapping the design into a library of building block cells and interconnecting them as necessary. That's what we do. Largely prefabricated, but components are almost configured in a variety of predefined configurations and all. Okay, let's see the advantages. Low NRE cost, high performance, low power consumption, less complex, small marketing time. The only disadvantage you will see is you will not have supporting tools to do all of this. Okay. And design constrained by prefabricated block available in library. So uh, your wafer is already prefabricated as per your need. So sometimes you cannot just alter your design. You have to follow what you already decided for. In the middle of the project, you cannot just do some innovation into it. Okay, so this is the cost to the volume comparison. Now, digital ASIC design flow. Now we are talking about digital ASIC design flow that we actually do on top of your structured ASIC. The disadvantage you fix using your digital ASIC design flow. So digital ASIC design flow is a flow that we use in our real-time semiconductor at the moment, at this current era, as you can see. So we have front-end design, back-end design, and ASIC fabrication, 3 stages. So the front-end design comes with design architecture, floor plan. The floor plan means the blueprint, starting with blueprint, and then you recruit all the resources, RTL design engineers, everybody, to start writing the RTL code. Okay, all this RTL design and verification will come under front end. Back end design is something you convert this RTL into gate level, netlist, and physical design engineers start working on it. So that is back end. And ASIC fabrication, once this is done, you move on to fabrication stage, where you give this your design that you have finally designed using all the design engineers and following the flow, and you test it on the wafer. And if real IC, you bring up the real IC and make sure it is working. And multiple wafers are getting tested. Based on the yield, your manufacturer will say it's working fine, we can go to the customer and to the market. Okay. So the front end design flow would be like this. You come up with like your iPhone, Apple, okay, or a Samsung phone, or you can say OnePlus. Okay, so that is your end product. So that becomes your design specification. So you wanted to design a mobile SoC. Okay, now the fabless companies, okay, will come to the fabs and ask, can you design and fabricate, or you can only do fabrication? I will make the design somewhere else. Okay, let's say MI is there, Xiaomi. Xiaomi will give its project, your mobile SoC design, to Intel or some other company. Okay, and it will say that I'll be using TSMC libraries end of the day, because I will be giving my IC to manufacture with TSMC. So use TSMC. If not, let's say you are giving it to Intel. Intel own fabrication and Intel own technology node has to be used. Then Intel will say, I can do design and manufacturing also for you at this particular cost. Then Xiaomi says, okay. Then Xiaomi becomes our client. Okay, our customer. Okay, now Intel starts recruiting the front end designers, or pulling out the resources. Okay, and start with a specification, what kind of IC you want. So you and the customer will both sit together. The client, Xiaomi, and Intel will sit together, coming up with the specifications, what can be done, what cannot be done. This can be done, and this is your duration. At this is your roadmap. Okay, in one year I can design your IC, and these are the stages that we segregate, and these are the deadlines that we follow, roadmaps. So we have to meet them. We give timelines and estimated timelines, and we stick to that. And we start with writing the design code. Okay, so you start with specification. For that, you write the design entry, the RTL coding. Once RTL coding is done, you give it to the functional verification engineer to develop the test bench. Okay, and verify this RTL code. If functionality is okay, yes, then you move on to DFT. If functionality not okay, you go back correcting the RTL code. But this is just for showing up. But what in reality what we do is, even if it is yes or no, it will come to the DFT based on the maturity level of the RTL coding. Let's say you have written RTL code for your SOC. The entire SOC will be not be written in one time. Okay, we start with the blocks. I mean, you're following a bottom up approach or a top down approach. Okay, so bottom up approach is something where you start writing the lowest hierarchy, the block level RTL code, and from there you move on to the subsystem. Next, you move on to the full chip. Okay, so block will be delivered by the RTL engineer to the function verification team, and if he verifies, let's say he says that the RTL has issues, but it is matured up to 50% or more, then okay, then we can use this particular initial RTL for DFT flow bring up, because for this particular project again every ASIC flow owner has to develop the flow. Okay, set all the libraries, flow, everything, and keep it ready so that when RTL reaches 100% maturity, okay, then the RTL will be finally tested at full configuration and delivered to the tester. Okay, so here the Bizer and BIST and JTAG insertion along with the DFT features. This is a built-in self-test mechanism and joint test action group. This is JTAG. This is a Fuchsia and IEEE protocol. Okay, both of these are part of DFT. Okay, so once the DFT insertion is done, we synthesize it. Okay, here what you are seeing here is an RTL flow. That means, see, generally there are two ways. Either you use a synthesized netlist to do DFT insertion, or you start doing insertion on a RTL. Okay, RTL means it is in still RTL code only. You did not synthesize it into gate level. Okay, so this, once you do DFT insertion RTL, then you give it to synthesis. So this will be from synthesis team. Certain companies will have separate synthesis team, or most of the time the physical design engineers will do synthesis, and they start from here onwards. Your what we call physical design work will start. The physical design work is to start synthesis, and you get the gate level netlist. He will do DRC errors, pre-layout, timing simulations, DRC checks, and all of this. Okay. Next, the chip functionality will be described in requirement and specification document. So whatever the Xiaomi and Intel has discussed in the initial during specification discussions, okay, what customer needs, that will be requirement, and what we can do, and what are the specifications of the IC, all will be documented, and we call it as a spec, requirement and specification document. Okay, so the targeted speed, power consumption area is also specified, everything. Okay, what we can do, at what speed we can achieve for this IC, what were the previous versions of this, what is your target, everything will be discussed. So system engineer conveys requirement in plain English to design team and verification team. Design team generates RTL code as per specs. Verification team generates test benches or test cases as per specs. Okay, so the design entry, the RTL design engineer will start work either by schematic capture or through HDLs like VHDL or Verilog, etc. So schematic capture is a old method. Um, as I said, the first design methodology. Okay, if you already have a previous version and we are just replicating it, then we directly take the previous version which is already taped in and came to the customer outside market. We take that schematic capture and we update on that. Let's say Qualcomm Snapdragon. Qualcomm Snapdragon has already released one version of 810. Okay, and they're going to release 811, which is almost similar with less changes. Then we'll just use the 810 schematic capture of entire SoC and just replicate it for 811 and add whatever the features you can add. Okay, so if not, you go with plain writing of RTL Verilog code and you start writing for the new design. Okay, the quality of final chip depends largely on quality of RTL code. So the efficiency of your RTL design engineers is very important. So if your RTL design engineer is writing the code efficiently, okay, it impacts a lot throughout the process. Okay, it minimizes the turnaround time in overall chip designing and testing. Okay, so your RTL code has to be perfect first. Okay, so there are some guidelines, design guidelines which should be followed. Design should be synchronous. Clock gating should be avoided. Flip-flop should be used instead of latches. Proper FSM coding styles should be used. But out of these, you compromise a lot. Majority of the time, your design will not be synchronous. You use a lot of clock gating cells. The flip-flops should be used instead of latches is the only thing that you use in real time. You use flip-flops. Yes, please go ahead. Someone has query.
Sir, synchronous meaning here, design should be synchronous mean.
Design should be synchronous means in terms of the reset clocks. Okay. So whenever you say synchronous, the only thing that makes your design asynchronous is that your reset or your clocks. Okay. So if your entire SoC is following a synchronous architecture, that means everything is synchronized. Your clocks, resets, everything is synchronized. Okay. There is no asynchronous reset network or asynchronous clock network. Okay. Right. So the 1 and 2 we compromise a lot. We cannot achieve this given the future architect design consideration. DFT it doesn't work with DFT also. Okay, and without clock gating you cannot achieve low power. Without clock gating there is no concept of low power designs. Okay, so you cannot compromise on this. Only thing you can do is flip flops, and you end up using latches a lot of times. Okay, when we start DFT basics, we'll understand where and all we'll use latches and what is the importance of latches. Okay, so you cannot avoid latches. FSM coding styles doesn't matter much, but majority of the time you use the industry standard FSM coding styles, so that wouldn't be much impact. So these are simple guidelines just to make sure that your RTL code is perfect, but it doesn't really happen in industry until I mean, only few companies follow this. They're very strict in what they want to do, and they achieve it. Given their long experience in the industry, with all the old good practices, they apply the learnings from the previous project failures or the disadvantage they see in the previous tape-ins. Okay, they improvise it and make it perfect in the next IC manufacturing. So I have seen so far is NVIDIA, Samsung, AMD, Qualcomm, Apple. They are doing very good, very good in the industry. Next, IP cores or third-party soft cores are used for standard blocks like processor, Mac, UART, etc. Okay, so IPs. This is very important, guys. Okay, let me explain here for you guys. You should know what is an IP. Okay, in semiconductor, IP, the term IP will be used uh, on a major scale. Okay, so the common word you will see is IP. Let's say this is your SOC. Okay, this is your SOC. In your SOC, I'm not sure I have shown you guys, but in the very introduction, I think I have shown you. Okay, so this is a high-level MT6739 functional block diagram. Okay, so in this particular SOC, each particular component or a peripheral will be from a different manufacturer. Okay, so this could be one moment. Okay, so this could be from coming from the Cadence, Synopsys, Micron. Okay, and the camera may be coming from a different vendor. Your processor inside MediaTek coming from a different vendor. Okay, so when a vendor, okay, third party vendors, okay, so you have uh, the vendors means, okay, third party, generally we call third party vendors. Okay, so third party vendors means these people who are specialized in designing a particular module. Let's say the counter. Okay, a certain group of companies is expertise in designing counter, so they will give you a IP. They will release their IP, the counter RTL code, everything related to counter in the form of an intellectual property. This is intellectual property belongs to some company. Okay, for giving you an example in real time, so Cadence is a company, EDA company, but it has a lot of IPs. Synopsys. Okay, so Micron. I'm taking Micron as an example. Let's say Micron is giving you a DDR. Okay, DDR is a dynamic data rate. Okay, if it is a low power, then you have LPDDR. Okay, so this is and module supporting your interaction between your CPU, okay, to the RAM. So let's say if your RAM is also coming from Micron, okay, then he will also give you the LPDDR, which is this part. Your LPDDR is a module sitting in between CPU and RAM, which will help you process the data from CPU and RAM. Okay, so generally LPDDR is supported by, I mean, it's provided part of your RAM. Okay, so Micron gives this LPDDR or RAM as an IP. So let's say this SoC is designed by Intel. Okay, now, and let's say this is an in-house project, Intel's own project. There is no other. It is not doing it for some customer own processor, for making it easier for you guys to understand. Okay, now for his IC design, he is designing mobile SoC. Okay, you need RAM in your processor, right? So you have your CPU coming, Intel own CPU. You need memory, RAM. Okay, so this RAM is coming from a third party, then it is an IP. It comes as an IP, intellectual property. Okay, and this IP is, everything is predefined. So your DFT, RTL, everything is done here. Everything is done. So this guy will give you whatever you want. You want RTL, you want netlist with DFT inserted. Everything he will give you. You just need to plug and play. You just need to integrate. Plug and play means you need to integrate. So the EDA tools will support integration of your IPs. Okay. Now, likewise, so I'm just explaining you what is an IP. Okay, there are two type of IPs. One is soft IP, hard IP. Okay. Now, soft IP is something, is a code. It's a Verilog code of some 30-bit counter or a 16-bit counter, which is efficient. You're taking it from some third party. Okay, so it's just a code. It's just a code, and it can be modified. You took it from somebody and you modified it, customized it as per your requirement. Okay, you can call it as a soft IP. Okay, and again, you have taken this RAM, right, from a third party, but you want to customize it at your end. What you do is you add a wrapper. Okay, what is this called? Wrapper. Any logic that you try to add to control this RAM from full chip level, okay, that will be at this level. Okay, so DFT engineer work is to integrate this RAM at this wrapper level. Now this becomes a subsystem. Okay, DFT engineer has to work on subsystem, and RTL see, I'm just not telling you all the process. RTL design will add wrapper, and DFT has to work on doing DFT at this stage, integrating this RAM at this level, and again at full chip level, integrating this to this full chip level. Okay, so this wrapper is also sometimes called as soft IP. The logic support surrounding the hard IP. Okay, the customizable logic surrounding the hard IP is also called as soft IP. Okay, I told you two examples. One is a code, already very low code or logic. Okay, you already have it, and that can be customized. Okay, as per your need. Either you're taking it from Intel itself, from a another internal group of Intel, or from a third party, which is customizable, that is soft IP. Okay, another soft IP example is the logic surrounded by the hard IP, okay, which you cannot change. That means you are not intended to change anything inside the hard IP. Nothing. You need to use as it is. You can also, you can do one thing. You can request Micron to say that, okay, support me. I'm using so and so technology node in my SoC. I want your Micron to support me in integrating this hard IP and any future additional feature you need. Okay, for this hard IP, you ask these people to do it. You don't do it at your end. Okay, this is a hard IP which cannot be changed. Okay, you have to just plug and play, use it. This is a hard IP. So all the sensors, analog sensors. Okay, your mobile phone has many sensors, right? Sensors, actuators, everything. Digital IP, analog IPs. Okay, so all these are IPs, which are hard IPs. Anything that you cannot change, okay, either it's a digital IP or analog IP, it's a hard IP. Okay, even the memories. You are using RAM, ROM, all these memories inside your SoC. You buy it from somebody. Okay, either Synopsys, Cadence, Micron, or Samsung. Then you just have to plug and play. RAM, they will give you everything needed for integration. Okay, this is called hard IP. This part is clear, everybody. What is soft IP, hard IP in semiconductor?
Yes, sir.
Okay. Okay, so IP.
Sir, I have doubt in
Yes.
previous PPT. Gate array, gate array. What is gate array, sir?
Gate
Gate array based design. Gate array based design.
at which stage? Which slide?
As ASIC design methodologies, gate array based design.
This one?
Yeah. Sir, what is gate array means? Is it same as MOSFET?
Yeah. So gate array is something that you already have fabricated your design. Mostly it will be in terms of designing memories.
Oh,
Okay, memories or FPGAs comes with CLBs, right? FPGA comes with the CLBs, complex logic blocks, right? You have predefined. You say that your FPGA is designed perfectly and it can perform these functionalities. You use it as per your need. You configure and it use it. And memories are straight away. These are memory cells, right? Let's say you are using a pen drive or a what called a SD card or a hard disk. It's a predefined, right? You don't need to write code, different code. It's predefined, right? Predefined
yes.
structure. So you just need to make sure that you design one cell and replicate it to how many cells you want. So that technology you fabricate it, prefabricate it. You tell the manufacturer that, okay, I am, this is my design methodology. I invented this low power memory cell. Okay, I want this to be at 16 GB, 24 GB, or 1 terabyte, whatever. Okay, so you tell the manufacturer and you talk to him that can you prefabricate it for me. Okay, so he will
Okay.
do that.
So we are like a customer
Yes,
for them.
yes, yes,
We will say that we'll set the requirements of our cell.
yes, yes.
Okay.
So everything, all majority of the time, what happens is your design this particular gate array ASIC. You predefine. I mean, you design your wafer with all the basic cells.
Mm.
Okay, basic cells. So once you have this die or a wafer with all the basic cells, once you have the die, you just need to make connections only as per your circuit.
Yes.
Okay, it will be
So we
simpler.
are giving this to a test bench or
So only cells will be already there. You just need to form connections from this cell to this cell, this cell to this cell based on your circuit, overall SOC circuit or whatever your design is intended. It will be less effort. So this can be done only for memories and FPGAs and certain things where your circuit is not complex or challenging. You cannot just prefabricate it. Okay. Apart from those scenarios, mostly people on a reusability or a predefined structure kind of SOC designs, they just go this in this way.
okay. Okay, got it, sir.
Okay. Okay, so IP cores or third-party soft cores are used for standard blocks like processor, Mac, UART, etc. So as we discussed that, now test bench. So test bench, as a yesterday in yesterday's session, I have shown you how a test bench is written for a small D flip flop. Okay, so we are talking about a small flip flop, but the verification engineer has to write the test bench for a larger modules, 64-bit adder, multiplex, not multiplexer, encoder, decoders, okay, IPs, okay. So verification engineers has to write for a larger test bench for a larger designs. So it is complicated. You write large test bench. It is complicated. That's why we verification engineers has the benefit of using system verilog and UVM methodologies, which will reduce the burden of writing the test bench. Okay, so these are the methodologies in verification that will reduce the burden of writing test bench for a larger designs. So it's simple. Majority again, tool does the majority of the work. Just you need to know what to change. Okay, it would be simpler for verification years now. Now, so what they do is they create a stimuli generator, and this is your module. Okay, and they will create output monitor to monitor it. Okay, so that is the way of writing a test bench. So the first test plan is worked out based on which different test cases are identified. Okay, how many ports are there, input ports are there, output ports are there, and which is the clock port, which is the reset port. Okay, and what are the data ports. Okay, any other test ports that you need to configure. Everything will be done in writing, generating the stimuli, and you need to monitor the output coming out of this whatever you have given stimuli, and response is captured in this monitor. So verification engineer designs this one and this one. Okay, but using the tool again. Okay, tool will do the part again where engineer has to support it, configure it. But certain let's say as I said, SV and UVM methodology has to use, right? So if we already have a flow enabled, you just it would be easier to modify and program the control registers and sequences, and just write the test bench. Okay, if you do not have, you get it from others. Let's say you are testing a DDR-IP. DDR-IP will give you the sequence. You just have to modify at your chip level at where you are testing it. Okay, and you can easily generate test plan. And for any module, okay, verification engineers will get the spec, okay, data sheet, the test plan of that particular IP that they're testing. Okay, so verification engineers have two types: those who work on SOC level, those who work on IP level. Okay, so IP level verification engineers will have everything coming as input from the IP datasheet. Okay. SOC level, what happens is you use JTAG flow, a JTAG and IJTAG flow. Okay, so that is a different. Now, for now, it will be complicated for you to understand. So I'm not going in depth as of now. So forget about, we are not verification course now. So remember that they write a test bench and they generate stimuli and check the response. So they have to write a test bench based on assertions. A signal is there, reset is there, when to assert, when to deassert. A clock is there, when to toggle and when not to toggle. So for that you need system Verilog programming of that particular RTL and a UVM methodology, which will give automation benefit of writing the test plan. So the functionality of RTL code is verified using test benches. It is called behavior simulation. Okay, so whatever he has done here, test bench, he has to verify it on the simulation platform. Majority of the time, you use simulators like Model Sim, Synopsys. Model Sim is from Tessent, and NC Sim is from Cadence, and Synopsys VCS, that is not added here. Okay, so VCS, it's a Synopsys. This is Cadence. This is Simons. Now Tessent Mentor Graphics is acquired by Simons. So Simons Model Sim. Now code coverage indicates how much portion of RTL code is covered by test vectors. Okay, let's say okay, this is your RTL code. Okay, so it has multiple modules, instances, logic, gates, everything. Okay, it is full of logic design. It is 100%. It is 100% logic design. Now verification engineer has to write test bench considering all the inputs, expecting a output. Right now, when he's writing test bench, he should make sure this entire 100% of RTL code is covered. That is called coverage. Coverage is equal to the number of logic design tested by the total number of logic design tested can be testable. Okay, so it can be testable. 100% testability is there, but you have you have reached only 50, 80, 90. Then coverage is also important. They have to reach certain target. Okay, so statement coverage, expression coverage, branch coverage, toggle coverage. So they have different variation of coverages in terms of reset line, clock line, the statements, how many statements are there in the design, in the RTL design, how many expressions are there. Okay, how many branches or instances are there. Okay, so they do all these coverages. Typically, a good test bench achieves more than 90% of the code coverage. That is true. Okay, so for functional verification, so far I haven't seen more than 96% of coverage in my life so far. Okay, 95 is really a good coverage number actually. Design for test. Now comes the part where you got the RTL, which is verified from the verification engineer and say, okay, at least 50% and above is matured in the earlier release. Why I'm saying 50% in the initial time is because I'm not sure I have told you before, but let's say, okay, your design comes with 0.0, 0.1, 0.2, 0.3, 0.4, 0.5, up to 1.0. That means these are generic number system where RTL maturity increases from 10% to 20, 30, 50, likewise. Okay. Here it is 60%. By 1.0, it should be around 95% or close to 100. So generally what we pick here is DFT will pick only at 0.3, 0.5, 0.8 and 1.0. Okay. Here let's say assuming 30% or 50% maturity of the design. Here 50 to 70% maturity. Here 70 to 85% or close to 90% and 85% to 100% maturity of design. That means if here at when you reach 100%, okay, this 100% you reach when DFT says okay, physical design team, structural design team says okay, verification team says okay. Okay, so when all of these teams says that I don't have any complaints with design, we have reached, DFT has reached certain test coverage and verification engineers reached certain test coverage. Okay, so at that time we say that okay, design can be freezed. If the design is freezed, okay, that means there will be not be any modification. This is the first tape in, which is called SOC tape in. Okay, next is manufacturing tape in, and manufacturing tape in or power on. So this is where your SOC is finalized. Design is, there is no change in the design. Okay, so this is how you work in the industry. These numbers are the numbers which they release when RTL is released. It is released to DFT or SD. Okay. Let's move on. This concept is clear, right? This is clear.
Yes, sir.
Okay. Moving on to design for test. Along with the user logic, extra blocks are added for detection of manufacturing defects. That's the role of DFT. We did not go into that. That's why just we are trying to explain ASIC flow. So this is our role as a DFT engineer. We add extra logic into the existing RTL logic, which helps in detecting manufacturing faults at early stages in the pre-silicon and post-silicon. Okay, so pre-silicon and post-silicon is design stage. When it is still in design stage, okay, it is pre-silicon. When it moved to CMOS design and it is going into tester, ATE, automatic test equipment tester, it is post-silicon. That means you are saying that your design is finalized and you are ready to give it to tester. This is post-silicon. Okay, so your pre-silicon and post-silicon, you do simulations at this stage. DFT will do lot of coverage activities and simulations and to make sure that there are no manufacturing defects. Okay. And in post-silicon ATE tester also, you directly test on the chip wafer. On the wafer testing will happen. Okay. So the sort test where your IC has to, whatever they design, that has to work and should give good coverage, which is 90% to 100% in between. So there is a target, there will be targets of 95, 98 and around that. So it has to reach. Okay. So either of the cases, whatever DFT generates patterns, test vectors, okay, stating that my design is 95% fault free or defect free. Okay, at pre-silicon level you call it as a fault free, at tester level you call it as a defect free. Okay, defect will be at a physical level, fault will be at a design level. You are at still in your laptop, you're trying to do something. This is at physical level on the chip. This is a defect, this is a real defect. Okay, now these patterns you do it with the pre-silicon netlist and post-silicon netlist, and whatever the patterns that you deliver on the post-silicon netlist to the tester, that is a golden test vectors or patterns. Okay, which will contain what is the content of test vector? Stimuli and response. Okay, so ATE will have comparator. So ATE will feed in the stimuli to the comparator. Comparator will check on the design with the existing golden response. If you in golden response, the AND gate output for a one output is 1, and in response it is 1, your comparator will, when compares the real behavior at the tester, I mean on the IC, is also 1, then it is passing. If you in the response it is 1 and in comparator you see 0 comparator output, then it failed. Okay, clear? Okay, right. DFT is a structural test, unlike dynamic simulation, which is functional testing, the verification testing. So functional testing, when you say functional testing, is always functional verification. Engineers, whatever the verification engineers does, that testing is called functional testing. DFT is a structural testing. Now DFT methodology, what are the DFT methodology we have is built-in self-test mechanism, boundary scan chain test, internal scan chain test. Okay, so there are many methodologies, but these are the prime. DFT advantages. DFT will give you the advantage of improvising more yield. You get more yield. That means your IC design is, the quality is more, right? So you are detecting the defects, the manufacturing defects early in the early stage, rather than on the tester. On the tester, it is on the wafer, the physical. If it is failed, your IC, you have to throw it. You have to discard that IC. That's a loss to the manufacturer. Okay. So to avoid that, DFT plays a major role. Make it easier to generate vectors because DFT EDA tools are so efficient. Reduce vector generation time. We do that part of tester. I mean, sorry, the DFT methodologies. Okay. Disadvantage would be okay. This is your IC. This is your length and breadth of your IC. This is your functional logic area. Okay, there will be ratio. 40% they leave it. Okay, 60% occupies your functional logic. 40% is intended to leave for the space to avoid any heat consumption. Okay, the near gate to gate near connectivity. Okay, so there will be some area. So let's say your SOC is intended for DFT. That means DFT friendly SOC. Okay, then they give you a good amount of area for DFT logic. Let's say your DFT logic is added like 10% to 20% on top of your functional logic. Okay, so this is area overhead. So now it became how much? 60 plus 20 is 80% you are occupying. So there is only narrow 20% only area available, the free space available. Okay, which will be used for the insulation and isolation and power shifters and all to avoid any heat consumption and power dissipation. Okay, so area overhead is the only disadvantage. Okay, I mean, we keep talking, there will be, we can bring in lot of disadvantages and advantages, but typically talking, the disadvantage would be only the area overhead. Okay, right. So I don't want to go so deep so that we are not aligned. I mean, it shouldn't be too much on a burden for you as you're going deeper. Okay, so I hope everybody's okay till this part. Shall we continue or continue to the next class? I can take up to 20 more minutes if you are okay. Otherwise, we'll call it a day. It's okay. You can say we are a team now. We have to survive for next 4 to 6 months. Tell me.
I'm okay, sir. You can continue.
I need everybody's agreement. Thank you.
Yes, sir,
Other-
you can continue.
Okay. So today's session is very important for DFT. Okay. We are moving on from very basics to semiconductor basics, which are very important. Okay. We are discussing about the flows. So I would encourage people to stay in the sessions active. I don't want people to drop off. If somebody want to drop off, you need to take a permission, ask me, then you drop off. Otherwise, it would be the courtesy or the meeting manners. Okay, not meeting the meeting manners would be very bad. Okay, because in real time, what happens is if you are in the meeting, in a scheduled meeting between managers or team members or other parties that you are working with the colleagues, you can't just drop without telling, notifying. So either you text it in the chat window of that meeting saying that I need to catch up with another meeting or I need to drop for some reasons and all. Okay. People don't just silently drop off. That's a bad habit in real time. They consider it as a bad practice. Okay. Next. So, built-in self-test insertion is one of the test methodology as we discussed. Okay, in the name itself, I think I'm not sure it is in engineering, at least for the BTech. I think there will be I'm not sure, I don't recall. At least in my academics, I have learned this in part of my master's. Okay, so built-in self-test mechanism is a test mechanism designed to test on its own. Okay, so it has everything. It has a stimuli generator, it has a comparator, and it will give you the output directly. You just trigger it, you enable the BIST from from the board at a board level. Board level means directly your IC. You just trigger it, just give the BIST enable signal, enable it once, done. It will automatically test the internal logic and give you the output. So you don't need to go inside and do all this stuff of testing. Let's say your mobile phone or a laptop or any electronic gadget which can be tested by the manufacturer or a technician. Okay, you go to the person and you say that my mobile phone is heating up, or it's blank. I mean, it's not working. Okay, you want him to check. Then he does some checks, right? He does some diagnostic runs on the mobile phone by connecting the phone to your USB or whatever the charging cable that you have. So the charging cable, the entry, that is a UART. Okay, so USB, UART, whatever the entry that you are giving, that from there your general purpose input output pins can be accessible. Okay, your in this diagram I will show you. Okay, so this is your mobile phone and this is your USB, right? So in order to access your entire phone, this is the only way. Okay, so this USB internally is connected to the GPIO, general purpose input output pins of your IC. So this is entirely motherboard connections. Somewhere you have this processor, somewhere you have GPU, display unit, all the peripherals and all. Okay, so this here, the ports which are the general purpose input ports here, okay, gives you access to what you want to access. You want to access the memory, you want to access the let's say we connect our mobile phone to our laptop. What will it show? It will show your RAM, your disk space, your photos, videos, whatever audio you have, you can copy it to your system, right? So you are getting access to the RAM. Similarly, you can access every other module through diagnostic tool. If this is a Samsung mobile, Samsung will have a Samsung diagnostic tool. Okay, if it is a Lenovo laptop will have a diagnostic tool. Okay, so using the diagnostic tools, you can invoke test methodology already inserted in that particular chiplet. Okay, so what you can do is you can test audio, you can test display, you can test memories, hard disk, everything. Every single component in your SoC can be tested and say that okay, it is working fine or not working fine. So which is not working, that can be either refurbished, or I mean it can be replaced, or it can be refurbished. The manufacturer will tell you. If it cannot be done, if it cannot be done, that means you do not have the future of DFT. Okay, if you have DFT future, you give the benefit of refurbishing and what we called replacing, reusing. Okay, so there are many benefits of DFT. You can directly replace it because DFT will give the benefit of isolation of this particular IC from the other ICs in the other components in the SoC or a motherboard. Okay, so this particular thing that you can replace, okay, you will only know when diagnostic tool is run and it says it passing or failing. That's how you can identify. So the diagnostic tool will have your golden patterns. Previously, I have told you DFT will give you the final post silicon patterns proving that my design is 100% or 90% testable. Okay, fault free. That patterns are fed into this diagnostic tool. Okay, so now Samsung S22 Ultra is there, Ultra phone is there. S22 Ultra is a model name. Internally, it will have some x-axis or so model number for this phone. This phone model, when it got finally coming to the customer after tested, okay, the patterns that were used for testing this will be saved in a database and will be provided as a diagnostic to the diagnostic tools. So post manufacturing, if you want to diagnose this particular mobile phone, this tool will use this particular golden patterns that we are used in during testing, okay, to verify the design again on the post silicon. Okay, this concept is clear.
Sir, can you repeat it, sir?
The whole or the last part?
The last part.
Okay, so the golden patterns that you deliver to the tester, the post silicon. In the previous slide, I have explained we deliver golden patterns, right? Pre silicon and post silicon, we deliver patterns to the tester that I told you, right? ATE tester. This is the tester. Okay, so on the tester, this IC is getting. I mean, whatever your design you have done so far, implemented, that you have given to the tester. So this is your physical IC on the wafer. Okay, this is getting tested. So you DFT engineer responsibility is to deliver the golden patterns. Golden patterns are something that final patterns. Golden patterns mean it will not be coated with 24 karat gold. Okay, these are final patterns. Final patterns or text vectors that has proven that my design is 95% to 100% fault free. Okay, so on when it is tested on the tester, it should meet the same number. Okay, this is a number where you observed at your end, designing end. When you give it to the on a silicon level, you should reach at least this number in between these two. Okay, and once it is finally made it to the customer, this tester, this IC comes to the customer, right? I mean, it's get shipped to the customers. Users are buying mobile phones now, right? After IC is getting into the market. Now, when a customer is having an issue, okay, he goes back to the test. He goes back to the technician. Technician will say if he has the availability of the diagnostics tool at his end, okay, then he will do it at his end. Otherwise, he will say we need to send it to manufacturing unit. Okay, it will get tested and they will get back to you. So they will do this diagnosis using these golden patterns that we delivered. Okay, okay, to check. Okay, what is wrong? Our patterns are for entire SOC, right? Your entire SOC, each module is tested. Your patterns have the test vectors, the stimuli or response captured for each every module inside your SOC. Okay, so all these patterns will help you diagnose each individual component post manufacturing. Got it?
Yes, sir.
Okay. Moving on. So the built-in self-test mechanism is one mechanism that you can directly trigger from the outside. Outside means the IC outside through this GPIO ports. You can directly trigger, and if you trigger, tool will perform all the tests because this is inserted by DFT engineer only. Built-in self-test mechanism is inserted by DFT engineer while the IC is being designed. Okay, so we have two methodologies. One is memory based and one is logic based. Memory based is to test the memories, RAM, ROM, RF registers, all these type of memories. Logic based is to test logic gates. Logic gates, sequential circuits, other than memories, everything, all the logic, which are in terms of transistors or gates that you see, the RTL code that you write, right? This is called logic based. Okay. We have only two types of logics, right? Logical gates and sequential logic in designs. Sequential logic comes where flip-flops, latches, counters, and all of this. Okay. Now, this is one methodology. You can do it. So this is a this is for memory based. This is your memory based logic. What you are trying to do is this is your SOC, the architecture. Okay, I mean considering this is your total SOC. From this level, you have all the primary input ports, right? This is the primary input ports and this is the primary output ports. Now, without DFT logic, that means BIST logic, what happens? You have direct connection from this to this memories. Your DFT logic will add a mux, additional mux logic, okay, where you will not touch the functionality and try to add the other input of the mux. Mux will have two inputs, right? So one path we will give it for the functional behavior. Functional behavior means the RTL intended logic. You don't change it. The other input of mux, it will be your scan, memory based or whatever, test logic. So you can give your desired input. Okay. So mux are added. This is a mux logic or any additional logic needed will be added at the inputs of these memories. Memory, address, read, data in control pins. Okay, you see this address data control. Okay, so here you see this FSM, data generator, address generator, control generator. This will be part of your memory based logic, which we add along with the muxes. Okay, and the output is provided given to the comparator. As the memory based is a simple design, and comparator is something that you know the logical behavior output tool knows, right? Tool will have the ability to compare. Let's say tool knows all the truth tables of every logical gate, memory, everything. Tool can do that comparison, and tool will compare the expected output to the generated output out of this logic. Okay, at this data out and drive out. So sorry, here data out will go into the comparator and it will compare the value, expected and simulated value. If it is passing, it is passing. If it is failing, it is failing. Okay, this is for memory based. Similarly, it would be for logic based. Okay, so we do use this. This is default. Memory based is default for every SOC. Logic based is used for few IC designs. Few IC designs we don't use because it is complicated during insertion and you need expertise. Moving on, JTAG insertion is the first. IEEE standard and test methodology invented, okay, long back, when there was no DFT at all. There was no test methodology at all. This is the first test methodology that was invented. Okay, so this methodology will just give you access to the boundary pins of the IC or your chiplet. Okay, so it will give you access to each and every input and output and internal connections of each individual component of your SoC. Let's say I have 20 to 40 components on my motherboard. Okay, so the 20 to 40 components in your motherboard are connected to each other, right? They do some, they are needed, the connections are needed for the, like, let's say the clock PLL output is going as input to the SoC as a clock. So you need that. Like I have shown you one image, right? This. So all these are connections. So your boundary scan logic will help you check the connectivity of each and every component or module to module, and also gives you the access of controllability of each and every primary inputs and outputs of your IC. Okay, for that there is a methodology called IEEE 1149.1 standard for boundary scan testing. This is called boundary scan testing because this is a boundary, right, of your IC. You can test each and every primary input and primary output before uh, before going to customer and after going to customer also. Okay, this we will learn later